Hello, everyone. In this last video, we'll wrap up the discussion about the singular value decomposition, and we'll put all together all of the observation that we did in the last video. They're summarized here, so let's just go through them very quickly. The setup for the singular value decomposition is a non-symmetric matrix A of size n by n. Of this matrix, we defined the singular values, which come by taking square root of the eigenvalues of A transpose A, which we saw it's a symmetric matrix with non-negative eigenvalues. So we can take their square roots. Additionally, from the matrix A transpose A, we also find a basis of eigenvectors. A transpose A is symmetric, so there's an orthonormal basis of eigenvectors, and that's what we called our basis VI. On the other hand, we defined the basis UI of vectors in Rm that are defined, well, some of them, for as long as we have singular values, are just defined to be singular vectors of the matrix A. The others come from a process of completing to a basis and then orthogonalizing by Gram-Schmidt and then normalizing. So we don't have a lot of information about the last few UIs. Now, let's just collect here some of the properties of these two orthonormal bases, U1 through UM and V1 through Vn. Some of them we've already seen, but it's good to have them all in one place. Okay. So whenever we'll work first with the indices for which a singular value exists. So when I is less than k, so sigma I is defined, we have the following two equations that are the equations that define singular vectors. We have one, the first one by definition of the UIs. That's the first equation is satisfied. The second one is something that we need to check, and it will turn out it's automatic from how we set things up. In fact, if we try to compute A transpose UI, that's A transpose of 1 over sigma I times AVI by definition of UI. So when I clean this up, I get 1 over sigma I on the outside. This is A transpose AVI, but VI is an eigenvector of A transpose A. So this becomes lambda I over sigma I VI. But remember that sigma I is the square root of lambda I. So when I divide lambda I by it, I get sigma I VI, which is exactly what we wanted to prove. So the definition of singular values and singular vectors are satisfied for I less than or equal than k. When I is strictly bigger than k, we have the two following properties. We no longer have singular values, so you see that these right-hand sides are replaced with just the zero vectors. And why is that true? Why is that true? Well, let's see. If I want to check AVI, I can do it as follows. I'll look at its norm instead, and the norm of AVI is AVI dot AVI. Well, but this is the same as VI dot A transpose A VI, but remember that VI is an eigenvector of A transpose A. So we have that this is lambda I VI dot VI. Now this lambda I, because I is bigger than k, is 0, because the lambda i's with I bigger than k are all of the eigenvalues that are equal to 0 in our matrix. So AVI is a vector of length 0, but then it must be 0 itself. So that proves the first line here. To prove the second, we have to be a little bit more careful. And we'll prove it in the following way. We have A transpose UI, which is a vector inside Rn. And we have a basis for Rn, which is given by the VJs, the vectors V. So we'll just compute A transpose UI dotted with every one of the VJs. And if we can show that this is 0 for all of them, then we're saying that A transpose UI is orthogonal to every vector in a basis, but then it must be the 0 vector. That's the only possibility. So let's try to compute this. Well, this is UI. I can move across my matrix times A Vj. Now, we know something about AVJ. In particular, well, let's see. When J is less than or equal than K, AVJ is equal to sigma J Uj. So this is equal to sigma J times Ui dot Uj. This is if if J is less than or equal than K. But let me comment a little bit more and push this a little bit forward. We're assuming in this inequality here that I is strictly bigger than K. So I and J cannot be the same, but the UIs are an orthonormal basis. So UI and Uj are orthogonal, which means that this must be a 0. So A transpose UI is orthogonal to all of the Vj with J less than or equal than K. Now let's try the other. If we have J strictly bigger than K, this becomes just UI dot AVJ, but we've just computed that every Vi with I bigger than K, so every Vj with J bigger than K is a 0 when you multiply by A. So this guy here is equal to 0, and so we get a 0 in this case too. In other words, A transpose UI is perpendicular to every vector in the basis, so it must be the 0 vector, which is what's stated in the second equation here. Okay, now that we have all the properties of these vectors, we are ready to wrap everything up in the following slide, which is about the singular value decomposition of A. So we'll do it like this. Let me define two matrices, V and U. These contain the vectors V1 through Vn and U1 through Un, the vectors that we've been with, the basis vectors that we've been working with. Observe the following thing. So let's try to compute A times V. A times V is a matrix whose columns have A times the column vector in V at every time. So that's just what's written here. Now, in the properties that we just computed, we saw that A times Vi is equal to sigma I Ui up until K. So the first K of these columns are equal to singular value times singular vector, just like so. And the last one are 0, again, by the property that we just proved. Whenever the index is bigger than K, A times V is 0. Okay, so A times V looks like this matrix here, whose columns are a bunch of zeros at the end, and they're given by the first K vectors of the basis U multiplied by the singular values. So now I'll write that in the following way. I'll define a matrix here. I'll call it sigma. The size of sigma will be the same as the size of A. Size A. But sigma will have one block up here that looks diagonal. We'll put a K by K blocks in here where there's the singular values on the diagonal and zeros elsewhere. If you do that, and you try to multiply these two matrices together, if you think about what you're getting is exactly the matrix that we wrote up here. The first column of this product will be given by the linear combination given by the coefficients in this first column here. Or in other words, the first column of sigma extracts the first column of U with coefficients sigma 1. and then the second column of sigma extracts the column U2, and so on. But then after you reach sigma k, then sigma will kill the last columns of U. So all of the UK plus 1 through UM here at the end will become zeros. So I'm trying to convince you that this equality is in fact valid. Think about it for a little bit, and maybe we'll do an example in a second. We'll do an example in a second, and you can see this happening there. But what we did here after this manipulation and using heavily all the properties that we just proved is that AV, A times the vectors of the matrix of the right singular vectors is the same as U sigma, where U is the matrix of the left singular vectors and sigma is the matrix that kind of looks like diagonal, but it's not, it's an m by n, and it has singular values in it. This is the content of the singular value decomposition. Remember that, to go from one expression to the other, you want to remember that V is an orthogonal matrix, so V inverse is equal to V transpose. The singular value decomposition tells me that A can be written as U times sigma times V transpose, where the matrices are given as we described above. U and V are orthogonal matrices of singular vectors, and sigma is a matrix of singular value. And I encourage you to think about where we started from. When we had a symmetric matrix, we had a diagonalization like this, PD, P transpose. We can't no longer do that. We can't use the same matrix on both sides when we want to diagonalize a matrix that is not symmetric, like this matrix A that we've been working with. But this is the next best thing. We have two orthogonal matrices, even though they're not the same, and we have a matrix that has a diagonal block in it, even though it's not diagonal. So it's as close as we get to diagonalizing with orthogonal matrices a matrix that is symmetric, that is not symmetric. Let's go back to our initial example, our little matrix A. The singular value decomposition for A is as follows. Well, the only thing that is missing, we computed in previous examples the vectors U1 and U2, and V1, V2, and V3. So we can just put them here. I'm not gonna rewrite them, but they're in the notes. The only piece that is missing from what we did before is the matrix sigma with its singular values. We know that the singular values of A are √6 and sigma 2 is 1. And we know that there must be a 2x2 block in here, which is given by this k equals 2 in this example. 2 by block diagonal here, and the rest of the matrix are all zeros. In this case, the rest of the matrix is just one last column. The size of sigma is the same as the size of A. So the singular value decomposition of A is written here. It's given by the matrix U times sigma, times V transpose. Okay, this is the last video of the class. Thank you for bearing with me up until this point.